Thank you again for joining today's Gen 4 International Forum webinar presentation on lead containing mainly isotope lead-208, new reflector for improving safety of fast nuclear reactors. The presenter is Dr. Evgeny Kulikov. Doing today's introduction is Dr. Patricia Pavier. Patricia is the Technical Group Manager of the Radiological Materials Group in the Nuclear Sciences Division at Pacific Northwest National Laboratory. She's also the chair of the Gen 4 International Forum Education and Training Task Force. I give the floor to you, Patricia.
Thank you so much, Berta. Good morning, everyone. It's a pleasure to have Dr. Evgeny Kulikov with us today here on his PhD at the National Research Nuclear University, MEPhl, in Moscow in 2010, and is currently the Associate Professor at the Institute of Nuclear Physics and Engineering. His areas of professional interest include improving fuel burn-up, nuclear fuel cycle, non-proliferation, and fast reactor safety. Currently, his scientific research is supported by the Russian Science Foundation. He lectures on theoretical aspects of nuclear reactors and conducts laboratory works on experimental reactor physics. He is serving on the Gen 4 International Forum Education and Training Task Force. So thank you so much again, Evgeny, to volunteer to give this webinar today, and I give you the floor. Thank you.
Thank you a lot for a kind introduction. And hello, everyone. And I would like to thank you to join us this day. Now I have a presentation for you. You saw the title. It is about lead, which contains mainly isotope lead-208. Such a lead is proposed as a new reflector to improve safety of prospective fast reactors. As you know, safety is very important and actually a #1 priority in nuclear field. And if we look at the respective types of generation for reactors, then 3 out of 6, that is a half, are fast. This idea that I will be speaking about is applicable for any type of fast reactor, sodium-cooled, lead-cooled, or gas-cooled. That is why this topic is very important and urgent. At this slide, you may see the outline of the speech. We will start with a review how to slow down chain reaction. After it, I show you how slowing down chain reaction could improve safety. First, in a simple case when there are no feedbacks, and then we will continue with a more real case when there are feedbacks in the reactor. And at last, we will look from where we can take this lead-208, sources of lead-208. So let us start with a review of how to slow down chain reaction. To start with, I would like to remind you that as a result of nuclear reaction, we get neutrons that are divided into prompt and delayed. And prompt neutrons are emitted by the fragments immediately. The fraction of them is over 99%. And delayed are emitted a bit after it, some time after it, some seconds. The fraction is less than 1%. Even if we have only a bit of them, thanks to their essential delay time, they help us to control a reactor. And comparing to spread of thermal reactors, the respective fast reactors are more difficult to control. That is because a lifetime of prompt neutrons here is 1,000 times shorter, as you see it here. It's not 1 millisecond as in thermal, but 1 microsecond. and the fraction of them is twice smaller as well. The idea of this speech is safety improvement by slowing down chain reaction. And here you may see how we can do it. Fast neutrons from the core should go deeply into reflector. You may see it here. And then they should have high probability to return to the core as a result of diffusion. In some way, we may call them delayed because they will go back with a delay time. Let us formalize these requirements to slow down chain reaction. Requirement number one is penetrate deeply into reflector. It means that Newton H should be as large as possible. Newton H shows us how far fast Newton travels from where it is born to where this distance is migration of neutrons at slowing down from fast to thermal, while this one is migration at diffusion from thermal to absorption. To fulfill second requirement, to have high probability to return to the core, this value should be larger than this value. In other words, the diffusion length should be larger than square root of Newton H. You see, the idea to slow down chain reaction is that fast neutrons go deeply into reflector and return to the core with essential time delay. Here you may see characteristics of chain reaction rate. To have a large Newton H, we need to have a reflector with large atomic mass, so something heavy. To have a large diffusion length, here, we need a reflector with small absorption. And for a long lifetime of a Newton, we also need a reflector with small absorption. Looking at these requirements, we may conclude that lead-208 is a good choice for a material of reflector because it is heavy, 208, and it absorbs very small, as you may see it at this slide. Here you may see capture cross-section of lead isotopes and some other elements. A natural lead consists of 4 isotopes: lead-204 here in black color, 206, 207, and 208. We can see that lead-208 captures less than any other lead isotope and even less than deuterium and graphite at thermal energy range. So it captures extremely small, actually. It leads to the following. First, Newton H and diffusion lengths are very large, as you may see it here. So it means that fast neutrons from the core will go deeply into reflector. This value is large, and it will go back to the core because this value is also very large and bigger than this one. If we compare it with natural lead, then we may see that although a Newton from the core would also go same deep, it would not go back to the core. Other elements here are the same as natural lead and graphite. Well, for it, a Newton cannot go very deep into reflector. Second, slowing down probability is high. It means that a Newton would go into reflector, and it will be slowed down there to thermal energy, and it will be saved. It will not be absorbed. For a natural lead, it is not the same because it captures higher. And third, as you may see it here, a lifetime of thermal neutron is long, which is very important for safety, as we see it soon. In lead-208, thermal neutrons live longer than in any other material of a reflector. This slide shows you albedo. Albedo is an important characteristic of a reflector. Albedo is defined as a ratio of returning to living neutrons. The maximum value of albedo is unity. It means that all neutrons leaving the core go back thanks to a reflector. This slide shows thermal neutron albedo on thickness of reflector. We may see that the larger thickness of reflector, the larger albedo. But at a certain thickness, there is a saturation, a limit. For a natural lead and light water, albedo is low. That is because too large capture cross-section of these elements. Heavy water is considered as best moderator thanks to very low capture, and due to this fact, it has high albedo. However, at thickness over 70 centimeter, lead-208 has even higher albedo, which is really impressive. It is even better than heavy water. So this slide proves that lead-208 is really very effective reflector. Now let us consider properties of lead-208 as a moderator. A good choice would be something that has large scattering cross-section and low absorption cross-section. Here at the top of this slide, you may see a composition of natural lead. Roughly half of it is lead-208, 1/4 is lead-207, a quarter lead-206, and just a bit of lead-204. Lead-208 is double magic nucleus with closed proton and neutron shells, and therefore its excitation levels are higher than for other elements, than for other isotopes of lead. They are higher than 2 MeV, while for other lead isotopes they are pretty low, below 1 MeV. That is why the lead-208 has a high threshold of inelastic scattering compared to other lead isotopes. As you know, the average energy of neutron that result from a nuclear chain reaction is 2 MeV. It means that there is no inelastic scattering of such neutrons on lead-208. Therefore, a neutron that leaks the core almost won't lose its energy by inelastic scattering on lead-208 and would go deeply into a reflector. At this slide, you may see comparison of moderator properties of different materials. First of property here is a logarithmic energy decrement. It describes average energy loss per a collision. It is not dependent on energy, it depends only on atomic mass. This value is small for heavy elements such as lead. It means that many acts of collisions are needed for a neutron to be slowed down on lead. Because of the low logarithmic energy decrement, moderating ability for lead is also low here. But integral characteristic is a moderating ratio that takes into account absorption. And as you remember, absorption for lead-208 is very low. That is why it results in a high value. We may conclude here that lead-208 is a better moderator than light water or beryllium oxide or graphite, and is inferior only to heavy water. Now let us see how these good properties of lead-208 help us to improve safety. This slide shows a contribution of neutrons with different lifetimes into reactor criticality. As already said, in fast reactor, prompt neutron lifetime is very short, about 1 microsecond here, as you see it on this axis. It is very short comparing to that in smaller reactors, where it is about 1 millisecond for PWR or CANDU type of reactors. Control of a reactor is possible thanks to delayed neutrons. Their lifetime is very long. It's 1 second or even tenths of seconds, but its fraction is very small. And reflector from a natural lead almost does not increase neutron lifetime, as you see it in brown curve. But if we have a reflector from lead-208 here in red, we can increase prompt neutron lifetime up to a delayed neutron lifetime. And the fraction of these neutrons is considerable. It's 34 beta, where beta is a fraction of delayed neutrons. And if we add a bit more of a reflector, it would add us longer time. This slide shows you peculiarities of reflector neutrons. These are neutrons that go back from a reflector. Their origin is prompt and delayed neutrons that leave the core, spend a relatively long time in reflector, and then go back to the core. Their fraction is much less than prompt, but much more than of delayed neutrons. Their lifetime is between prompt and delayed, which is very important for improving safety. These neutrons spend a relatively long time in reflector and return to the core at lower energy comparing to a typical value of prompt and delayed neutrons. It's important to say that reflector neutrons have input into nuclear chain reaction only after returning to the core, which means that there is always some dead time when they can't affect reactivity. This is also important for improving safety. As these neutrons come from a reflector, their inputs into nuclear chain reaction mainly at the edge of the core, where effects of reactivity are lower comparing to center of the core. Also, we may change the amount and energy by changing reflector geometry and material. Finally, reflector neutrons play the role of additional delayed neutrons. This slide shows you importance of reflector neutrons considering reactor runaway. Here you may see 3 options. Option number 1 on the left is critical reactor with a reflector. It is a critical here multiplication factor is equal to a unity, and its components are multiplication factor on prompt neutrons, delayed neutron fraction here in red, and input of reflector neutrons here shown in green. Second option is runaway on delayed and reflector neutrons. If there would be no reflector neutrons, then a reactor would be supercritical on prompt neutrons, which would mean a rapid runaway. But thanks to reflector neutrons, even insertion of a reactivity that exceeds delayed Newton fraction does not lead to a rapid runaway, as you see it here. It is still subcritical on prompt neutrons. The third option on your right is runaway on prompt neutrons, only if there is an insertion of a very large reactivity that exceeds delayed Newton fraction plus the input of reflector neutrons, then yes, there is supercriticality on prompt neutrons. Here you may see an example to understand how Newton lifetime is important for safety. Let us consider fast reactor runaway without feedbacks induced by step insertion of reactivity for two cases. Reflector from a natural lead here in red color and reflector from lead-208 here in blue. If reactivity does not exceed delayed Newton fraction on your left here, then there is only a little advantage of lead-208. But if reactivity does exceed delayed Newton fraction, then in this case, we may see that if we have a natural lead, reactor power increases by 500 times just in 3 milliseconds, that is almost explosion, while in the case of lead-208, much slower. That is a big difference, and lead-208 as a reflector in fast reactor could slow down chain reaction and improve safety. Now let us continue with a more real case when there are feedbacks. According to the model of Newton flash, if inserted reactivity exceeds delayed Newton fraction, beta, then this is a state of prompt supercriticality. Heat does not have enough time to reach the coolant, and that's why only Doppler effect has enough time to act, and duration of Newton flash is proportional to a Newton lifetime, while energy yields is independent on Newton lifetime. All this is correct if we have a reflector of natural lead, but when we have lead-208, Newton lifetime increases by 3 orders of magnitude, not 1 microsecond, but 1 millisecond. And duration of Newton flash would increase proportionally, is about 1 second. 1 second is actually even more than time constant of fuel element, the parameter that indicates how fast heat is transferred from fuel to coolant. And so in this case, part of the heat has enough time to reach the coolant, and negative coolant feedback has enough time to act in addition to a Doppler effect. So we may conclude that if we have lead-208 as a reflector, there would be not 1 but 2 feedbacks, Doppler effect and negative coolant feedback. Here you may see fast reactor power at the Newton flash. Inserted reactivity is twice as much as delayed Newton fraction. In the case of natural lead, A Newton lifetime is about 1 microsecond, so while in the case of lead-208 about 1 millisecond. That is why processes are 1,000 times slower here, and peak power is 1,000 times lower. When processes are slow, there is enough time for the heat to be transferred from fuel to coolant, and about a quarter of the heat would be transferred to the coolant. It leads to the fact that temperature of fuel increases not that quick, 1,000 times slower, and reaches a lower level because part of the heat is transferred to coolant. Finally, here you may see one more comparison. These are dependencies of relative power growth rate on reactivity. If we consider fast reactor with natural lead as a reflector, then insertion of reactivity about delayed Newton fraction would mean almost explosion. You may see it here, very strong increase of power, while lead-208 makes the reactor much safer. A runaway would happen as slow as in thermal-conduit type of reactor. Finally, we consider from where we can get lead-208. Actually, lead-208 is final product of a radioactive decay chain of thorium, while lead-207 and 206 are accumulated due to decay chains of uranium. Lead that is produced in radioactive decay chains of thorium and uranium isotopes is called a radiogenic lead. And a relative content of lead isotopes in radiogenic lead, it depends on age of ore and admixture of natural lead. So we can get radiogenic lead from thorium and thorium-uranium ores. This slide shows ore deposits containing radiogenic lead. Here we consider ores that have high content of thorium because lead-208 is accumulated due to decay chain of thorium. You may see that there are ores in Brazil, in Australia, in Ukraine that contain a radiogenic lead with about 93% of lead-208. Let's see if such a composition enough to keep good properties of lead-208, or would a small presence of other lead isotopes ruin them? In other words, do we need to enrich lead, or can we just get it from the earth? To make a decision, let's consider dependence of required reactivity on asymptotic period. This value is period of time during which reactor power changes approximately 2.7 times. Long asymptotic period means that transient processes are slow and reactor is easy to control. So this area is easy to control area, while short asymptotic period means that processes are rapid and the reactor is difficult to control. Red curve number 1 indicates the case of a beer core. Insertion of reactivity that even slightly exceeds delayed Newton fraction leads to a very short asymptotic period, as you may see it here. And it means that power increases rapidly. Curves number 2 and 3 correspond to adding a reflector from a natural lead. And as you see, situation is almost the same. Insertion of reactivity that even slightly exceeds delayed fraction leads to a nuclear accident. Green curve number 4 indicates a case of reflector from a radiogenic lead that is extracted from thorium ores. So that is more or less a real case. A symbiotic period is dozens of times longer, but still it's rather short. Pink curve number 5 indicates a case of reflector from lead-208. In this case, as you see, a symbiotic period is almost 1 second. That is slow enough for emergency systems to react. That is good. Curve number 6 is an imaginary case when capture is equal to 0. You may see that there is almost no further improvement comparing to curve number 5, and it means that lead-208 has small enough capture and there is no need to look for other materials that exceed it in properties. Enrichment plants in Russia are able to enrich lead up to the level of 99.8% of lead-208. It means that enriched lead would still contain 0.2% of lead-207. This isotope has a rather large capture cross-section, and even its very small content has a noticeable effect. As you see it from the curve number 7, you see we added just 0.2% of lead-207, and comparing to curve number 5, it looks more difficult to control. So the conclusion here is that it seems that we should enrich lead because what we have from the Earth, curve number 4, is not enough for systems to react. One more issue to solve is how thick the reflector should be. This slide shows a Newton lifetime in fast reactor with different lead reflectors. Parameters are fraction of lead-208 on this axis and thickness of reflector, which is presented by different curves. You may see that half a meter reflector is not able to prolong a Newton lifetime, even if we have high value of lead-208. 1 meter reflector is able to prolong a Newton lifetime by at least an order of magnitude. Combination of 2 or 3 meter of reflector and high quantity of lead-208, which is here, is able to prolong a Newton lifetime by several orders of magnitude, approaching 1 millisecond. This value. There is no sense to make the reflector thicker because, as you see, after 3 meters, all is the same. So here we may conclude that it's reasonable to use enriched lead of thickness about 2-3 meters. The conclusion is that a new approach is proposed to improve nuclear safety of fast reactors thanks to slowing down chain reaction. Lead-208 as reflector in fast reactor can considerably prolong lifetime of prompt neutrons by 3 orders of magnitude. That it would be about the same as in thermal type of reactors. Low Newton lifetime and short time constant of fuel elements substantially improve safety, even if we insert a reactivity that exceeds delayed Newton fraction. I would like to thank you for joining us, and if you have something to ask, please do it now. Thank you.
Thank you very much, Evgeny. While questions are coming in, we'll take a look at the upcoming webinar presentations. In September, a presentation on the Gen 4 coolants quality control by Dr. Christian Bloche out of CEA of France. October, passive decay heat removal system by Dr. Farmer with Argonne National Labs in the USA. And in November, the Czech experimental program on MSR technology developments by Dr. Euler with the Research Center in the Czech Republic. As a reminder, the presentation today is being recorded, and yes, it will be available to watch again or to share with others. The link will be provided on the Gen 4 International Forum webpage at www. I don't know if I can rattle that right off. That link will be posted in the emails that distribute after today's presentation. If you have questions, please go ahead and type those in now. Okay, there's a question. How does lead-208 influence neutron spectrum?
How does lead influence neutron spectrum, right?
Yes.
Well, yeah, I don't think that I have a slide to show a comparison of neutron spectrum that is formed in bare core and in the case of the core that is reflected by a natural lead and by the lead-208. Well, yeah, sure, it would make it a bit more thermal, but not that much, because lead is a heavy element. So a neutron, it would not be slowed down to thermal, and the reactor would still be fast type of reactor.
Thank you. How expensive is it to enrich lead-208 to the desired level, including removing lead-207?
Yeah, it's a good question. So this information about enrichment lead in Russia and up to what level they can do it, we asked it and they answered us only up to what level they can do it. But when we also inquired about the price, there was no answer from them. So I just think that maybe it's industrial secret or something else. So we don't have any info on that, sorry.
In your opinion, which kind of Gen 4 system is most suitable for these reflectors?
Well, as I said at the beginning of the presentation, it should be applied to any type of fast reactor. There are three of them among generation 4 systems. It's lead-cooled, gas-cooled, and sodium-cooled. In all these three types, it's applicable.
Did you assess the impact of slowed down neutrons returning from the reflector on power peaking at the edge of the fast core?
Sorry, and power peaking?
Correct. The question is, did you assess the impact of slowed down neutrons returning from the reflector on power peaking at the edge of the fast core?
No, I don't think so. No. Power picking. I would write it down. I would as on power picking of the edge. Okay. Could you tell it one more time, please, Berta? On
You bet. I've also, hopefully you'll be able to see it.
can I see it?
Yeah, if you look in your control panel, there should be a pod that allow you to see the questions. And then I've also shared it on the chat pod with all. But the question is, did you assess the impact?
Yeah, I can see it now.
You see it? Okay, great.
Yeah, did you assess the impact of slowed down neutrons returning from the reflector on power picking at the edge of the fast core? No, the answer is no. Unfortunately, we did not do it yet. Perhaps we should. Yeah. Thank you for this. Yeah.
Have you considered reactor control from the reflector?
Have you considered reactor control from the reflector? Could you specify what do you mean? Reactor control from the reflector.
So Craig Smith, if you're still listening, can you please clarify your question? In the meantime, there's a question in an MSR reactor, which is using thorium as fuel. Is there a possible interaction between the fuel and the in situ production of lead-208 as self-moderator?
Interaction between the fuel and lead-208?
Correct. The in situ production of lead-208 as a self-moderator.
In a molten salt reactor. Okay, in a molten salt reactor, which is using thorium as a fuel, is there a possible interaction between the fuel and the in situ production? Well, actually, I don't think so, because it takes time for accumulation of lead-208. It accumulates in nature due to a long decay chain and some reactions that are part of this chain. They happen during a very long time. So I don't actually see how we can do it in the core while we have this type of fuel. Anyway, there is enough of lead now in the earth, so there is no issue if we have it enough or no. Yes, we have it, enough. The issue is only how cheap or not cheap it is to extract it, to enrich it.
Thank you. Let's see. The thickness of reflector would result in a non-negligible effect on neutron lifetime is significant, larger than 1 meter. Have you done any evaluation or optimization that accounts also for the impact on the size of reactor?
I'm just looking for this question. Yeah, I see it. The thickness of reflector that would result in a non-negligible effect on neutron lifetime is significant. Yes, right, more than 1 meter. On any evaluation optimization that also accounts for the impact on the size of the reactor. No, this research is a fundamental research that was done during about 1 year, and we did not go yet that far. So here it's just a demonstration how to do it, and of course many aspects should be considered in future. That's of course for sure.
There's another question on cost, but I believe the answer to that is probably the same as before in that it is unknown. The cost to enrich lead-208 from at 98% from natural lead, but before you indicated that you weren't sure of that.
Yeah, well, enrichment level is 99.8. Is 99.8. Yes, but we don't know the price because we did not get any reply from the company that does it.
Could the control rods be located in the reflector instead of the core?
Well, in principle, yes, but their impact would be not that effective, not that strong, because, as you know, the number of neutrons and reactions is much lower there. Normally, they are located in the core. Well, you may do it in reflector, but effectiveness of such an idea, I don't think would be very high.
Thank you. I think that's all the questions. We've managed to go through the whole list. There's quite a few today. Thanks to everyone for your participation. That's always such a great indicator of interest in the topic. We appreciate your participation.
And I also have some that we should think about. I will write them down. Thank you for your feedback.
It's a plan, Evgeny. I'm planning to do that. We will talk about that with the Education and Training Task Force in a few days. I wanted to thank you again, Evgeny, and thank you to the audience for all these very good questions.
Thank you.
Okay, goodbye.
Okay.
Thank you, everyone.
Good day.
Bye-bye.